Okay, this is our lecture on section 15.2, how to take integrals over general regions. So, suppose we have some weirdly shaped region. I'll call it R, sometimes I'll call it D. I switch back and forth. R for region or D for domain. And we want to do the double integral of some function f of x, y, dA over the region. Now, there are a couple ways to do this. The way that I like is to put a bunch of rectangles over it. We have already shown how to do integrals over a rectangle. And so if we did that, we integrated all these individual rectangles, then we could add them up, do the integral of each one, and it would be a slight overestimate. But then we could make the rectangles smaller, and so that would cut out some of that overestimate. So like, our first guess was we did a rectangle like this, but then we'll split it here instead, so we get rid of this extra stuff. Another way, the way that I think our book, or at least a book does, would be to put a big rectangle around it, maybe call that D, and then define a new function, capital F, piecewise, which is little f when xy is in D, or in R, sorry, and 0 for everything else when it's not in D, and then do the double integral of big F over the larger rectangle D. I'm not wild about this way of doing things because this function, capital F, is not continuous. There's a big drop off. But either way, we get an answer. We can define how to do this integral. But in this class, we usually do it with antiderivatives anyway, so most of this is just theoretical. If you ever go on to study measure theory, which has a lot of applications, so you might, the question being, we've got some function and we want to integrate over some region so we can add up everything. How do we do it? And so you usually start by saying, well, let's start with a rectangle. That's an easier way, and then find out how to adjust that to more complicated ones. So, okay, we are still recording. That's good. Okay, so let's do some examples here, or let's talk about how we can do this. So, let's say we want to integrate 2x squared y dA over the region R. R is bounded by y equals 3x squared and y equals 16 minus x squared. Now, I said this in class the other day, but I'll say it again because we'll make this mistake a lot, is that if the limits of integration are constant, that is the little numbers that go on the integral, if they're constant limits of integration, then we're dealing with a rectangle. But this region is not a rectangle. In fact, let's see what it looks like. So this is a pretty common problem, would be to say, give you a region, give you the bounds, and figure out how to translate into a double integral. So we've got 3x squared, so that's like this. And I've got 16 minus x squared, which would be something like this. And so what is the region bounded by it? What region is enclosed by these two? Well, it's this. So everything else goes out to infinity. So we're looking for a region that does not go to infinity, a region that we could put a circle around. That's what bounded means. And that's inside the two curves. Let's go ahead and label these. This is y equals 16 minus x squared, and this is y equals 3x squared. So, we know what the function is z. In fact, we can say z equals 2x squared y, and that's kind of like the ceiling. So, we have this floor plan being this oddly curved shape here, and above it the ceiling is at a height which is determined by multiplying x squared times y times 2. This integral would represent the volume of that enclosure that we're creating. So now what we want to do is do this as a double integral, an iterated integral, and we need to either dx or dy first. And so one of the big tricks here is figure out which one would make sense to do first. Put that back. That's like that. Okay, so I think a good start would be to figure out what the intersections here are. So let's set these two functions equal. 3x squared equals 16 minus x squared. So 4x squared is 16, x squared is 4, so x is plus minus 2. And if you plug that in to either one of these, you will get 12 as the y value. Which is a good way to check that you did that right, because if you plugged in your x and got different y's, that would mean that you did something wrong in the solving and you need to go back and do it again. So, there are two options. Now, if we go from bottom to top, let's pick a specific x. So we'll just say this is x. And we go up. Well, x is sandwiched between 16 minus x squared on top and 3x squared on the bottom. So what you would do then, if you want to do it this way, is you would... I'm sorry, what am I saying? This is y, not x. Y... The vertical coordinate is between those two things at each point. We're saying no matter what x is, if we pick an x, then we can use those two functions to tell you what the limits on y are, even though it's changing the whole time. Now, on the other hand, what if we decided to go left to right? Well, we'd have to cover the whole thing. So when we do this, we'd go from the left side of 3x squared to the right side of 3x squared. Or actually, no, we'd have to solve for y. I guess we'd have to say x equals plus or minus square root of y over 3. That is, I just solved this equation, divided by 3 on both sides, and took the plus or minus square root. So x would have to go from negative square root of y over 3 to positive square root of y over 3. But then I'd hit this top part, and then I'd have to switch. I'd have to say, okay, what about this other function? Then I have to say, well, x squared goes from plus or minus square root of 16 minus y. And so you'd have two different double integrals. You have to do one double integral for the bottom part and another double integral for the top part. So I think doing y first is easier in this case, because it's always going to be 3x squared on the bottom and 16 minus x squared on the top. And the name for that is a type 1 region. So type 1 is the type where you want to do y first because it's always the same on top and bottom. And the left and right are just -2 and 2. Type 2 would be the other way. Don't bother memorizing this. I never remember it myself. I really don't care if you know the names of the things. Oh, I still need that. I really don't care if you know the names of type 1 versus type 2. The point is that sometimes you want to do it one way and sometimes you want to do it the other way. So, we're going to do y first. So we'll do dy, where y goes from 3x squared on the bottom to 16 minus x squared on the top. And then we'll say dx. Now the idea here, and sometimes it's a little hard to visualize, but is that when you do this first dy derivative, it's going to smash the y variable down into nothing. Because really what we've got here is a three-dimensional shape. We've got x, y, z, and we've got this weird curved shape here, so it's like this way and this way. And so it's like this, and then we have to go up. So we have a... I can't draw this in 3D. I'm bad at 3D drawing. I warn you, the 3D drawing is going to get important pretty soon. You could type this into GeoGebra, 2x squared y, and see what the shape looks like. But once we do the first dy, essentially what we're doing is we're taking this y variable and smashing it all against the xz plane. Some points are already on the xz plane, so they don't change. Some points are very far from it, so they change too. They change a lot. So now we would end up with an xz where the z will be based on, well, we'll get rid of the y, so it'll change to, well, let's find out what it changes to. What about x, though? The one thing I know is that the x will not change, so it'll become -2 on the left and 2 on the right. And this drawing part I'm doing here you don't have to do. I'm just trying to give a visual of what's going on. So x will go from -2 to 2. Okay, so we need to do the y integral first. So we'll get -2 to 2. And then from y equals 3x squared to y equals 16 minus x squared of, let's see, the integral of y is y squared over 2, so 2 times x squared times y squared over 2. I guess those will strike out. Dx. So now we need to plug in for y. So we'll get -2 to 2 of x squared 16 minus x squared minus x squared 3x squared dx. So notice what happened here. I just plugged in where I saw y. I plugged in this, plugged in this. The x squared did not change. It did not get plugged in. Hey, apologies for the kind of awkward cut here. I made some algebra mistakes I had to cut out, so I skipped one step, but I'm sure you can figure it out. Okay, so let's work this out. So it becomes -2 to 2 of x to the 6th minus 32x to the 4th plus 256x squared minus 9x to the 6th dx, which then becomes, we can combine the like terms, -8x to the 6th minus 32x to the 4th plus 256x squared dx. And then let's integrate this. It would become from -2 to 2 of -8 x to the 7 over 7 minus 32 x to the 5th over 5 plus 256 x to the 3rd over 3. Then we plug in, so we get negative 8 over 7, 2 to the 7th minus negative 2 to the 7th, minus 32 over 5, 2 to the 5th minus negative 2 to the 5th, plus 256 over 3, 2 to the 3rd minus negative 2 to the 3rd. And then you just type this into a calculator because trying to get this as a fraction is kind of a pain. Eventually, it comes out to 663.2-ish. It's rounded. Now, on a test, I would never expect you to do all this arithmetic. If you were to get to this here, that would be a suitable answer. Though I probably wouldn't give you one that's that complicated. So for the rest of these, I'm probably going to skip over the grunt work because you've all taken Calculus 1 and passed it, so I'm going to trust that you can do one-variable integrals. I more want to focus on the setup. So let's do another example. Find the volume of the solid below the surface f of xy equals 2 plus 1 over y, and above the region R in the xy plane bounded by y equals x, y equals 8 minus x, and y equals 1. Okay, copy that down because I'm going to erase it. So, how do we do this? Well, that's not a straight line. Let us first figure out what R is. We said we've got y equals x, so that's this line. I got y equals 8 minus x, so that's this line. Lines are all wobbly today. That's fine. And we've got y equals 1. That's here. Okay, so the region R must be this triangle here. So, in this case, if we went up first, the switch is here. So if we went up, we'd have to switch at that cusp, meaning we have to a double integral for this left side, and then another double integral for this right side. So this time I think it makes more sense to do x first. X will always be x equals y on the left, and if we solve this for x, x equals 8 minus y on the right. And notice we had to solve these for x because we are getting rid of x first this time. Again, you could do vertical first, but you'd have to do two separate double integrals, so it's easier to do horizontal first. And that's what makes this a type 2 region. And I don't care if you know the names, but just understand that sometimes you want to do x first and sometimes you want to do y first. So, the ceiling, z, was 2 plus 1 over y. So we're going to say dx, x goes from y on the left to 8 minus y on the right. And then what does y do? Well, vertically, y The minimum for y is 1. Now what is the maximum? Well, let's set those equal and solve it. We have y equals 8 minus y. So 2y is 8, so y is 4. So those are your bounds for y. Okay, so the setup is done. Let's go ahead and do this problem. Yeah, because once you've got the setup, that's like 70% of the problem, and I mean that literally. On a quiz, I'd probably give you like 7 out of 10 if you just set it up right, even if you didn't do the integral. So 1 to 4, so the x integral, so we will go from x equals y to x equals 8 minus y of 2x plus x over y. Those are both constants with respect to y. Or with that, I mean with respect to x. And the way to check is to say, well, if I took the partial x derivative, what would this give me? It'll give me 2 for this. It'll give me 1 over y for this. So we are essentially doing partial integrals. We are undoing the partial derivatives. So this would give us 2 8 minus y plus 8 minus y over y, bracket this, minus 2y plus y over y, dy. So this, let's work this out. This becomes 16 minus 2y plus 8 over y minus 1 minus 2y minus 1 dy, which is then from 1 to 4 of, let's see, 16 minus 1 minus 1, so that's 14. Let's do the y's first. Negative 2y, negative 2y, so that's negative 4y. Then 16 minus 1 minus 1, so that's plus 14 plus 8y to the minus 1. So I have these in descending order. First power, 0 power, negative 1 power. And then this one's actually not too bad, so I'll go ahead and finish it off. We'll get 1 to 4 of negative 2y squared plus 14y plus 8 ln of absolute value y. So that becomes negative 2 times 4 squared plus 14 times 4 plus 8 log of 4 minus negative 2 times 1 squared plus 14 times 1 plus 8 ln of 1. Natural log of 1 is 0, so that term is gone. And so this reduces down to 12 plus 8 ln of 4. And you could simplify this in a couple ways, but I think this is fine. Eight log 4 is the same as 16 log 2, for instance, but that's no problem. Okay, so let's do a few more. All right. So double integral along r of xy dA, where r bounded by y equals x minus 1, y squared equals 2x plus 6, y equals... Oh, no, sorry, I don't want to say any more yet. Getting ahead of myself. Okay, so let's graph the region. So there's always going to be your first step is to graph the region of integration. So let's see. Y equals x minus 1. It's like this. Y squared equals 2x plus 6. Okay, now this is a parabola that's going to open sideways. So I think it makes sense to solve this for x, just to figure out what the parabola would be. It'd be y squared minus 6 is 2x, or 1/2 y squared minus 3 is x. So this is a parabola with a vertex of negative 3, negative 3, that was right the first time. Negative 3, comma 0. Because if we plug in 0 for y, that would have to be, that's the lowest y could, and x is 3. Yeah, to minimize y squared, we'll plug in 0 for y, and it'll give us negative 3 for x. So it's like this. So again, which type is going to be? Well, we want to mark the intersection points. Say, if I was going up, then I'd have to switch at this intersection point. But if I'm going left to right, I never have to switch. So I want to do dx first. So that is, I think it's called type 2. I need to do dx first. And so if you're doing dx first, then your curves have to be solved for x. So this curve here would be x equals y minus 1 plus 1. Sorry, add 1 to both sides. And this other one we've already solved, x equals 1/2 y squared minus 3. So those are our limits on x. So we're going to do double integral of xy. We'll do dx first, where dx will go from 1/2 y squared minus 3 up to y plus 1. What about y? Well, we need to figure out what is the smallest y can be and what is the largest y can be. And again, we want these to be constants. Like I said, this first integral dx is sort of like, imagine smashing this thing horizontally so that we now only will have y and z. It'll be a one variable integral. So let's see. Let's set these equal then. Y plus 1 equals 1/2 y squared minus 3. That 0 equals 1/2 y squared minus y minus 4. Or 0 equals y squared minus 2y. Did I do that? Hold on, no, I'll check that. Is something wrong here? No, that's right, minus 8. So this factors into y minus 4, y plus 2 equals 0. So the solutions are negative 2 to 4. Okay, so the hard part's done. We then want to, let's say this is from negative 2 to 4, and this is from x is 1/2 y squared minus 3 to x is y plus 1. We do the x integral, gives us x squared over 2 y dy. And this becomes negative 2 to 4 of x squared over 2 y plus 1 minus 1/2 y squared. Wait. Oh, screw up. Little screw up. This happens. X is the thing we're plugging in for. Negative 2 to 4. So it's y over 2, y plus 1 squared minus 1/2 y squared minus 3 squared dy. And so this one is very long. According to my notes, the final answer is 36. If you want to work that out and check to see that that's right, you're welcome to it. But at this point, this is just grunt work. So I will say, if you're not good at doing just basic integrals, this would be good practice. But if this is the sort of thing where it seems really simple to you, it's probably a waste of your time just to go through all the grunt work on this. I'd say, from a mathematician perspective, this thing is solved. It's just a matter of going through the motions to get to the end. All right. So let's do some more examples then. Let's do something a little more challenging, perhaps. Okay, so find the volume of the tetrahedron bounded by x plus 2y plus z equals 2, x equals 2y, x is 0, and z is 0. Now, there are a couple things we need to do with this. And so, what I'm going to say is I'm going to want to make two different sketches. So we'll want a 3D sketch and a 2D sketch. So the 3D sketch showing the volume, what the shape actually is, and the 2D sketch showing the region we're going to integrate over. Now, I'm not sure which order to it. I'll do step 1 is 2D sketch. You got all this copied down? Okay, let's go on. So the idea is really what's happening with the volume is we are really doing a triple integral of the one function, where we would do dz first. Like that. And so I'm going to assume we have already finished that. We've already done the z integral, because if we did that, we would get f of xy. And so we're going to project onto xy plane. So we had the function was x plus 2y plus z equals 2. So the projection would be z equals 0, because in the xy plane z is 0, so it becomes x plus 2y equals 2. And the other function was x equals 2y. Well, that's already got no z in it, so it's already projected. So this defines our floor. If x plus 2y equals 2, that function goes through 0, 1, and 2, 0. And then the other function, x equals 2y, or y equals x over 2, if you'd rather write in that form, go like this. This isn't bounded, so we say, what were the other things they told us? Well, we said x equals 0. So x equals 0 is the y-axis. So this is our region. Now, for step 2, I'm going to want to do the 3D sketch. And this is kind of optional. Sometimes you can skip this part, but I'm going to do it anyway just for practice anyway. So the ceiling was z, let's solve that out, equals negative x minus 2y plus 2. So I'm going to draw it kind of like this. Now, I know that's not how I usually am drawing 3D pictures, but it's okay as long as it follows the right-hand rule. So if you point your fingers at X and curl towards Y, your thumb will go in the direction of Z. So we are just sort of rotating it so that we can get a better view, which is the intercepts here would be 0, 0, 2. If I plug in 0 for Z and Y, X would be 2. And for Y, it would be 0, 1, 0. You just work that out. Plug in 0 for 2 variables and solve for the third one. So that gives me 0, 0, 2, 0, 1, 0, 0. Hold on. Let me make sure I'm doing this right. Sorry, the Z should be a -2, shouldn't it? Yes, that was the trick. Okay, no, it shouldn't. What am I talking about? No, I guess that's all right. Okay. But, all right, so can I draw this? All right. There is also the x equals 2y to draw. So x equals 2y in the plane would look like this. And so these things would meet at this point 1, 1/2, 0. Because that is a point that solves both of them. And you could do this by plugging in 2y for x. You would get z is 2. And so the picture looks kind of like this, where we have this plane is our ceiling. X plus 2y plus z is 2. Our sidewall here is x equals 2y. And so at every point in this triangle here, we go up to the x plus 2y plus z equals 2 as our ceiling. So I warned you that the drawing is going to get tricky, and it is. And there are times when you'll have to do some trial and error just to figure out what the bounds are. I would encourage plug this into GeoGebra and just take a look at the different orientations. Anyway, what we have now, we know z is our ceiling, and it's equal to -x minus 2y plus 2. So -x plus 2y minus 2y plus 2 dA. Now, what about x or y? Which one do we want to do first? It looks like we want to go vertical first. So the top would be y equals -1/2 x plus 1. And the bottom would be y equals x over 2. You can just solve out that first one to get what y is. So, y goes from x over 2 at the bottom to -1/2 x plus 1 at the top. And then, so that's dy. And then x will go from 0 on the left to, I'm guessing the intersection point is 1. Let's see, if I plug in 1, y equals negative 1/2, 1 plus 1, that's 1/2. And the other one, y equals 1 over 2, that's also 1/2. Okay, so it's 1/2. No, it's a 1, I'm sorry. We plugged in 1, we got 1/2. So x equals 1. You just set these equal to each other and solve it. I just did a guess and check. Okay, so we get 0 to 1, and then we get from y equals x over 2 to y equals negative 1/2 x plus 1. And so we'll get negative xy minus y squared plus 2y dx. So now let's plug that in. We will get integral from 0 to 1 of, let's see, negative x, negative 1/2 x plus 1 minus negative 1/2 x plus 1 plus 2 negative 1/2 x plus 1, big brackets, minus, big brackets, negative x, x over 2, minus x over 2 squared plus 2 x over 2. And then you would do a bunch of expanding here, and you would eventually get to this reduces to, surprisingly, 0 from 0, 1 of x squared minus 2x plus 1 dx, which ends up as 1/3. All right. So like I say, the drawing is usually the hardest part in this, especially when we get into 3D. And I wish I could say I had some secret technique that makes it easy. I really don't. You just have to try to practice, because we're going to get some weird shapes and you have to figure out what order to do them in. We've got dx, dy, and dz. And so there's 6 different orders you could do depending on, you have to try to figure out which one's the easiest. All right, let's do an example of a reordering. So, let's say I was given this problem. 0 to 1, x to 1, x to, yeah. That 1 is in a weird place, but sine of y squared dy dx. Now, I look at this and I think, I don't think I can do this problem. I see this y squared in the sign. I'll try a u sub. U equals y squared. Then del u over del y is 2y. So I can say du is 2y dy. But there's no 2y there. So there's nothing I can combine to absorb in and become part of the du. Or if you are the type to solve out, dy equals du over 2y. If I plug that in, I'll have this 2y here that doesn't cancel with anything. So this problem cannot be done in the form it is. But I remember Fubini's theorem. It says that if I'm continuous on the region, and sine y squared is always continuous, then I can switch the order. So there should be a way to switch this into sine y squared dx dy. And I know it's tempting to just switch these two, but that won't work. Because remember, our rule said the last integral always have constants on it. If we just switched them, we'd have an x on the outside, so our final answer would have an x in it, and that's no good. So what we're going to do is sketch what we have. So what are our limits currently to say? They say x is less than or equal to y is less than or equal to 1. That's what this is saying. dy is between x and 1, so y is trapped between those. So let's draw that. So we've got y equals x as the first one, so it's this. And y equals 1 is the other, so this. And then it says x goes from 0 to 1. So 0 is less than or equal to x, less than or equal to 1. So there's x equals 0. And x equals 1 just happens to be the same as the intersection point. So this is our region. So if we want to do x first, well, we can say that, going left to right, x starts at 0. And it ends at y. So we can say x ranges from 0 to y. And then y ranges, the lowest y is 0, the highest y is 1, 0 to 1. So then let's do this integral. Let's try this now. dx first, sine y squared is constant, so we can say x is 0 to x is y of x sine y squared dy. And that becomes 0 to 1 of y sine y squared dy minus 0, so that's fine. And now we can do the u sub. We can say du is y squared, or sorry, not du. U is y squared, so du is 2y dy. So I'm going to put a 2 here and a 1/2 here to balance it out. And so this and this combine to make du. 1/2 integral of sine of u du. And I know there's another way to do it that a lot of you do, which is dy is du over 2y. It'll amount to the same thing because the y's will divide out and you're left with a 1/2 outside. So, you know, I don't always do it the same way. I learned it a different way than a lot of you did. Okay, what about the limits? Well, y went from 0 to 1. U equals y squared, so u will also go from 0 to 1. So that becomes 1/2, 0 to 1. The antiderivative of sine would be negative cosine of u, which is, so we'll get 1/2, or let's pull the negative out, cosine of 1 minus cosine of 0. So it's negative 1/2 cosine of 1 minus 1. And cosine of 1 does not simplify. It's some irrational number that can't really be easily described. So this is your final answer. So that is a trick. If your double integral does not seem doable, you can change the order and it might just work. But you have to draw the sketch and work out what the new limits are. You can't just switch them automatically. You have to figure out and you have to solve for the other variable if you're going to do that. Alright, so we're almost done. I want to discuss a few of the properties of integrals that are useful because there are times when you're not going to be able to work an integral directly, so you have to get a little creative. So first one will be the sum rule. If you have a double integral of f plus g dA, and a lot of times we don't bother writing out the f of xy and g of xy. We just write f plus g and assume you know that xy is the inputs. It's the same as a double integral of f dA plus double integral of g dA. You know, a lot of these are the same as the rules for one variable integrals. And the constant multiple rule, if we have a constant f dA, we involve the constant all the way out, same region, of f dA. Together, these two properties are called linearity. It's saying the double integral is a linear operator, which means you can split sums and you can pull constants out. If you take linear algebra at some point, this will come up all the time, the concept of linear operators. So this is just saying the derivative is a linear operator. Okay. Monotonicity. It just says if f is less than or equal to g on all of r, then the integral of f over r is going to be less than or equal to the integral of g over r. If you think about the volume, this kind of seems obvious. If they have the same floor plan, but one has a higher ceiling, it's also going to have greater volume. A decomposition of domain. So this is stated that if R is a union of two smaller r's, and R1, R2 do not overlap except at boundary, then double integral of f dA on R the same as double integral of f dA on R1 plus double integral of f dA on R2. That one's more complicated in words than in pictures, so visually it's pretty easy to understand, I think, which is to say, if we have some big region R, you find a place to split it into R1 and R2, you just integrate over those two separate regions and add them together, and it's the same as integrating over the whole region. And that's, we have to make sure the R1 and R2 don't overlap. They have this line in the middle where they're touching, but that's, a line has no area, so it doesn't count. Couple more properties. If we do the double integral across some d of the one function, that's the same as the area of d. If it were a triple integral, it'll give us the volume, but we're not at triple integrals yet. So we can combine those two, or a couple of these, to say that if we have f is between some small m and some large m on all of d, well, the monotonicity says we can do... what just happened? Sorry, my notebook program just did something weird. I must have pushed a button that it didn't like. Sorry about that. If m and m are bounds for f of x on all of d, well, monotonicity says we could do the double integral for each of them. And then the area function says we can, well, the linearity says we can pull the m out. And then this double integral says it gives us the area. So this becomes m times area of d less than or equal to the double integral across d of f of x, y, dA is less than or equal to capital M dA. Let's give an example of this in practice. Estimate double integral of e sine x cosine y dA across a region D, where D is the circle centered at 0, 0 with radius 2. Now I look at that thing and I say there is no way I can do that. Sine x cosine y as exponents. If I try to u sub, it would just fall apart really fast. This can't be done, at least not by any method I know. So instead I'm just going to say what are the bounds on this. Well, sine x and cosine y are both always between -1 and 1. So we can say the product here, sine x cosine y, is also between -1 and 1. So that means we have these bounds. So then e to the -1 is less than or equal to e to the sine x cosine y is less than or equal to e to the 1. And now we can put double integrals on all of these. And so this becomes e to the -1 area of D is less than or equal to the double integral d e to the sine x cosine y dA less than or equal to e times area of D. What is the area of D? Well, it's a circle with radius 2, so pi r squared. The area is 4 pi. So this becomes 4 pi over e, less than or equal to this double integral, less than or equal to 4 pi e. So that is a pretty broad range, but at least we have an idea. The integral is somewhere between these two real numbers. Okay, so that covers everything. I would say the quiz is almost certainly it's going to have something to do with finding the limits of a region or drawing a region and working it out. That's the main thing you had to do, was figure out how to set up double integrals. So focus on that, and I will see you on Monday.